Hello, everybody. My name is Sergej Kranjc. I'm from young company Thermodrone from Slovenia, where we incorporate drones and satellites and other modern technologies into the food production, into agriculture to reduce the use of pesticides and fertilizers. Today, I will present you our practice, our work in practice in the field of precision farming, which all started in year 2017 in collaboration with our local university from Slovenia, with University of Maribor, with Faculty of Bioengineering and Life Sciences. At first, let's take a look a little bit about what precision farming is by definition, and what are some pre-requirements. And later on, we will talk about what was our process of incorporating this technology into practice, and what was our learning curve, if may I say so. So, by the definition, the precision farming is some kind of a concept of management of farms with a focus of optimization of resources. We have in our minds especially seeds, fertilizers, and pesticides, with the final goal to increase the yields for farmer, to decrease the environmental pollution, improve and maintain healthy environment. So precision farming are actually not just modern nowadays modern technologies. For an example, modern machine, but are also optimization of resources according to the actual needs and reasonableness based on available data, the way of working. So the farmer's habit needs to be improved. I'll not say changed, but improved to accommodate this precision farming concept. So again, the goal is to reduce the environmental impact and to increase the resource efficiency and improve social, economic, and market competitiveness of producer or farmer on the local and global markets. But of course, to gain the maximum benefits in precision farming, it is the machinery is very, how should I say, it is very good to have the modern machinery that supports different advanced functionalities. For an example, we are talking about modern fertilizer spreaders, modern plant seeders, and modern sprayers. So they can really make precise final treatments and final execution of tasks and plans on the field based to the defined tasks that were defined based on the available data from other data inputs. So this type of smart machinery needs another smart piece of equipment which is installed on the tractors. These are the special tractor terminals that are connected to the smart machine via one bus called ISO-bus. It's a standard connection that connects this terminal with the machine, and on these tractor terminals, all the data, all the tasks are imported and defined so that on the field, machine carries out tasks as autonomously without user intervention. But of course, to do this, there is also another thing needed, and this is the global navigation satellite system, because the machinery needs to know its current position so that it can carry out the defined task for each specific micro location or position, if we define it like this. There are a couple of different providers of global navigation satellite systems. Maybe most commonly known is American network of satellites called GPS. These satellite navigation systems are of, how should I say, different occurrences, different resolutions. For an example, just plain GPS or GLONASS or Galileo or other satellites provide accuracy of around 5 to 10 meters. For an example, it depends on the location where you are. But for majority of cases, for an example, for spreading the fertilizer, this accuracy is more than enough. But for precision selective spraying of pesticides and, for an example, for precision variable seeding rates, for precision planting, this is not sufficient. So therefore, there are different attitudes of how we can improve this accuracy. Most commonly known is, for an example, with referencing to the ground stations, and with referencing to the ground stations, we can achieve the accuracy of up to a couple of centimeters, which is more than enough for these type of applications. So here is one not so smart example of farming equipment. It's a fertilizer spreader, but I must say that this basic equipment can be used to some extent as well to practice these precision farming techniques. But of course, really to the limited extent and on smaller fields, and with some other requirements as well. So, how did we start incorporating this in practice? It all started in year 2017, where we met with one local farming company. Actually, we have started small talk about the drones in practice. So we were also experts in the field of drones before that in power line industry. But we were not present in agriculture with this technology yet. After small talk with our local farming company, they have mentioned that no one is actually practicing this technology in practice. There is no real service provider in nearby markets and in local market that would integrate this technology to their daily processes, because we must take into consideration that all these modern technologies, modern machinery, and modern data inputs from satellites and drones generate complex data structures that are not so easy to understand for farmers that are in majority of cases not IT experts. So these things needed to be really simple and easy to use for them, so that they would really get the best benefits, the maximum amount of benefits possible of this technology, without sacrificing their daily routine and without due to the lack of the knowledge. So we have started a collaboration with them. Of course, we needed the expertise from agriculture area, where our faculty for bioengineering and life sciences came in. And from then on, we have made a really good progress. So just one basic information of how based on what we are doing, is that we are actually using the optical sensors from drones and satellites. These are multispectral sensors that are recording the deflected light in different wavelengths from the plant. And the plant has one really interesting way of showing us when it's under the stress or when it's healthy. It shows the biggest difference in light reflection in some of those wavelengths, especially in near infrared wavelength. And based on this data that acquired with drones and satellites, we then calculate special vegetational indexes, which shows us uh, the the stress areas, depression areas on entire field, and the healthy areas. Of course, from this, we cannot detect and we cannot say for sure what is the cause of these depression states. It can be due to the, I don't know, pests or diseases attack. It can be due to the irrigation problems. It can be due to the lack of nutrients in soil, soil structure, etc., etc. So this just shows us the general picture of the crop. Based on that, we are then performing crop scouting on field to detect the real cause of these stress areas. And for an example, if we take example of fertilization of wheat cultures, if we eliminate the occurrences of pests and diseases, and we know for sure that this is due to the differences, for an example, in soil or in soil structure or in nutrients in soil, we then perform fast nitrogen tests on field so that we can define how much of nitrogen application needs to be done in each area. For an example, in this picture here, we can see, I don't know if you can see my mouse pointer. We have divided this entire field to two different areas, and in this kind of scenario, we perform short, fast nitrogen tests in, for an example, in just this red area and in this, how is this, orange or what color is it area, and based on the measured values and the data from nutrition levels in nutrient levels in soil and so on, we then define the fertilization plan. This fertilization plan is then exported into the data types that is suitable for integration into the tractor terminal that we have seen before. And when the data is successfully integrated into the tractor terminal and the connection of terminal and in this case, the fertilization spreader is successful, the predefined fertilization plan is then automatically carried out on the field. So the user, the tractor driver, does not need to do anything. Actually, it just starts the execution of this fertilization plan at the start when he arrives on the field, and that's it. Everything is carried automatically by itself. Here, for an example, is the presentation of how this works in reality. So we can see that the fertilizer spreader knows its position, and based on this position, actually the terminal calculates everything, and based on this position, the amount of fertilizer is variably applied based on the predefined fertilization plan. With this, we can achieve two things. For an example, if we have pretty heterogeneous fields, so that means that we have a lot of sand areas and a couple of sub areas with more quality soil. We can decrease the amount of fertilizer in these areas because the fertilizer gets unused. It just goes into the water, into the groundwater. Actually, we have with this we have produced the environmental pollution, and we have thrown away the money just into the groundwater. So here in this use case, we can generate short-term savings that have no negative effect on the final crop yield. But in the cases where we have more homogeneous fields, we do not lower the use of lower the amount of fertilizer used, but we arrange it more efficiently. So, for an example, in cases where on almost all fields, we can see some kind of stress, depression states, and so on. And if we see this in early stages of fertilizations, we can redistribute the actual amount of fertilizer so much that we can achieve the better final yield with how should I say, with leveling the crop. For an example, in early stages of growth stages, if the crop has some depression states, we can get a bigger amount of fertilizer in more depressed states and smaller amounts or more healthy states. And in second fertilization phase, we can already observe the leveling of the entire crop, which on the final yields can produce more level yields, which we have already done in practice, and we have proven this with using the yield maps as well. So here is one perfect example of what I just said. Here is pretty homogeneous field, but due to the little differences, almost half of this field was under the stress. And using this technique to decrease the fertilizer amount in green, more healthy area in first and second fertilization phase, and to a little bit increase this fertilization amount in more stressed phase, we have achieved to gain around 1 ton per hectare bigger yield in this stressed state as per previous years, as per historical data. So actually, there was no short-term saving on the fertilizer cost in this case, but it was a long-term benefit at the end of the season at harvest time. We have also performed some different measurements for protein content and other parameters, because we also wanted to know if we can plan the harvest time more efficiently to gain more optimal contents of the protein and other stuff to get better market price at the sales point. So basically, this is how we can use this technology through the growing season and harvesting season, but it is also useful in after harvest time. In this slide, we can observe the fast nitrogen tests that are performed during growing stages for fertilization phases. But based on the depression states that we can observe during crop growth, we can predict, actually our proposition was that the crop by itself shows us the best in what state is the soil by itself. So based on that, we have, after the harvest time, we have defined two or more different areas with those depressions, where were the worst depressions, where were the a little bit better, and where was the best soil. And based on that, we have performed target soil samplings. we have compared this to traditional soil samplings. For an example, in this field that we can see here, we would in traditional way we would, for an example, take the soil samples in, I don't know, Z patterns or something like that. But in this case, we have performed also the target soil samplings. For an example, we took the soil samples from yellow areas first, and then another soil sample was taken from this orange area. And after the analysis, we saw that the target soil sampling showed us difference of one class in soil nutrient contents. Based on that, we have then prepared basic fertilization plans, so that basic fertilization was done really due to the actual needs by each sub area on the field. So our conclusion was in this case, and also in other cases, that if we take this approach, we can level the soil quality on the field and optimize the costs on the long run. For an example, if we just use the traditional methods, we can, on the long run, we can get even more, even less nutrients in poor areas, and we can, I don't know, maybe over fertilize the areas which are already in the good states. Of course, this everything needs to be consistent with the final yields. Here we can see one example of the yield map that we have generated. The goal is to merge, to integrate different data sets, data inputs from yield maps, from soil data, soil passport data, from even from weather data and so on, so that we can, based on this, perform as precise next steps as possible, and to eliminate possible long-term damages and possible negative outcomes as much as possible. So here's our concept of how we are doing everything, and of course, as already mentioned before, all these different data inputs and so on generate pretty complex data structures, and usually farmers are not the IT experts to understand them, and usually they do not have time to dig deeper into this data. What does this mean, and so on. So our goal is actually to integrate all these into one easy to use service or solution, so they really don't need to bother with the technical aspects of this, and they can use these technologies to really the best extent as possible. So I would like to thank you for your attention. That would be all from my side.